We can now continue with the study of the location of roots of the equation, which is given in the form f of x is equal to 0. Previously, we looked at how to locate the roots of the equation using the change of sign method. And you're saying that you draw a table, then you keep on substituting the values of x in the function f of x. Wherever you see a change of sign between two values of x, then you can make a conclusion that wherever there is a change of sign, there is a real root of the equation in that interval. Here we can also locate the interval within which the roots of the equation lies using the graphical method. We're going to use the graphical method. And the graphical method is also subdivided into two. There is the single graph method and the double graph method of locating the interval within which the root of the equation lies, and also locating the actual root of the equation. We can locate the actual root of the equation using the graphical method. So the graphical method is categorized when we are using a single graph method and also a double graph method. So let us first look at the single graph method. One, the single graph method. In the single graph method here, you draw only in one graph. You draw only one graph. And you plot a graph of, you draw your x-axis, you draw the graph of the function f of x on the xy axis. So this is the x-axis, and this is the y-axis. Then when you plot your graph, of course you first draw a table. When you're having your function, then you draw values of x and the values of f of x or values of y. Then you get the corresponding values of x, you get the corresponding values of y. Now when you plot the values of x and values of y, then you draw your graph, only a single graph, where the graph cuts the x-axis. For example, if this is the graph f of x, when you plot these points in the table or the xy, where the graph cuts the x-axis, then this is where we locate the root. This is the root of the equation. And if it is the interval AB, then you say the equation the equation has a root in the interval AB, and you can locate the root. And the root, it is where exactly the graph cuts the x-axis. If it cuts the x-axis like 2 times, if it cuts the x-axis, you plot your graph. Then it cuts the x-axis like 2 times, like this. Then this one here will be a root. Also, this one here will be a root of the equation, meaning that the graph has, the equation has 2 roots. If it cuts the x-axis 3 times, it means that the equation has the 3 roots. So wherever it cuts the x-axis, you come here and read the root. If that when it cuts the x-axis in the negative axis, the roots are not on the positive. In the negative axis, on the negative axis, x-axis, also it can cut it, and also this one here is a root. So if you draw a graph, then it cuts the x-axis 3 times, cuts here, all these ones are roots of the equation. So the graphical method can be used to locate the real roots, the actual roots of the equation, and it can also be used to locate the interval where the roots of the equation are expected to lie. By plotting the graph and see where the graph cuts the x-axis, then you locate the interval. Then here we will say that the graph has a root in the interval AB, because this is where the cuts interaction between A and B. So as the interval x is equal to A and x is equal to B. So the root has an equation in the interval x is equal to A and x is equal to B. And if you are required to locate the actual root, then you can read the value which is there, depending on the scale of the graph. Then you read the actual root of the graph. That is the single graph method. So we can also see how you can locate the interval or locate the root of the equation using the double graph method. Double graph methods. And in the double graph methods, this one involves splitting. You split the equation. It involves the splitting of the equation into two. For example, if you have your equation, for example, you have the equation a x power n, then plus maybe 2x. This one can be a power, this one can be, but you can generalize and use b, and this one is equal to 0. So if this is your equation, then if you wanted to use the double graph method, what we do, we split this equation into two. And how do you do it? We move one of the terms this side. Like right, this is plus bax. You can take it on the other side and say, now this is axn equals, when this one crosses the cosine become negative bx. Now we will have two equations. You split the given equation into two, like this one here, axn plus bx is equal to 0. You move this one on the other side and becomes negative bx. Then on this side, so you mark this one, you can call this one down. You have y1 equals to axn, then you have y2 is equal to negative bx. So when you plot, then you draw your tables. You will have y1 is equal to axn, then you have values of x, you have values of y1. Then you have also y2 is equal to negative bx. Then you have values of x and the corresponding values of y2. Draw your tables and you have the corresponding values. Corresponding values of x and the corresponding values of y1. Values of x, corresponding values of y2. So that when you plot these graphs, you put them on the same axis. This is the x-axis, and this one here it is the y-axis. You plot it. Now you plot the first one as the y1. For example, you can take this shape. And we said now this one here it is y1, we are not very sure, but we shall plot that two graphs. Then you can plot another one like the x, the negative bx, this one here y1 is equal to ax power n. Then this one here it is y2 is equal to negative bx. So where these two intersect, that's why you take the roots. And if the interval is a and b, then if you are really required to locate the interval where the roots of the equation lie, then you can locate the interval. And this is the roots intersect between the equations, the equation of y1 and y, graphs y1 and y2 intersect between a and b. Then you can make a conclusion that the equation has a real root between the interval a and b. And if you are really required to locate the actual root, you use your ruler and you have the point where these two graphs intersect. Then you locate the roots. But they can still have more than one root. They can still have more than one root. Like for example, you can draw. For example, if you this one here it is your y2 is equal to negative bx. Then this one here maybe it is like this. Like this. Then it means that if they intersect here, there will be a root. For example, it is interval AB. Then they can also be here, and this is C, this is D. They also, where is the intersection of these graphs? This one. When they intersect at this point here, then you can also, this one here is the root of the equation, this one is the root of the equation. So that what means that the equation has two roots in the interval AB and also the interval CD. But it can intersect two times in the same interval. meaning that the root has the equation has two roots in the same interval, but wherever the equation is the curves or the graphs intersect, that's where you locate the root. So that is the method of locating the root of the equation using the two graphs. So the questions, some questions are specific, they require use graphs, it means that you have to split the equation, then you plot those two graphs. But some of the questions are not specific. They say use the graphical method and locate the interval within which the root of the equation lies, and after locate the root of the equation to the given number of decimal places. Maybe one decimal place, four decimal places. So usually, if the question has not specified the number, the method you should use a simple graph because it is simple. Because it is simple to use. But it's most of the questions, some of the questions they specify. Use graphs, means that you have to split the equation into two. Then you draw the two graphs, y1 and y2. Where they intersect, they say they intersect in the interval between x equal to and equal to b. Where they intersect, you locate the root for the x-axis, and that is the double graph method of locating the root and locating the interval where the root of the equation is expected to lie. So we can use this example here using the single graph method. In the single graph method means that you're using only one graph to locate the interval where the equation lies, and also where the actual root of the equation lies. Now we are looking at the single graph method. Now using a suitable graph, locate the interval within which the roots of the equation 2x squared plus 3x minus 3 lies, hence locate the roots to two decimal places. Now what we do, this is our equation. This is our equation, y is equal to 2x squared plus 12 minus 3. Then what we do, we choose an interval. Like as I told you previously, when we are choosing an interval, we don't choose values which are far away from 0. When you see, or when you choose values and you see now there is no, for example, in the single graph method, where the root lies, there will be a change of sign. The change of sign will be like now when you see here, when you substitute in the 0 here, you are having negative 3. Substituting in the 1, you are having 2. Means that between the 0 and 1, there is a real root of the equation. When you substitute negative 2, why you are getting negative 1. Substituting negative 3, why you are getting 6. So you are substituting all these values of x in the equation, substitute 0, substitute 1, getting their corresponding values of y. You are using a single graph. So when you see that in this interval you have not obtained any change of sign, but here there is a change of sign from negative to positive, so means that in between x is equal to negative 2 and x, there is a real root of the equation. So when you see that you are not seeing any change of sign, you keep on adding the interval. You keep on adding. For example, if there was no change of sign, we would add here maybe 3 or 4, but you don't go very far because the roots will always be very close to 0. All the equations which I've been dealing with at this level. So what we do, we come and plot after drawing our table very well, substituting in the values, then we go and plot a graph. Now when you are plotting the graph, make sure that at least here you are using the 2 centimeters. Those are 10 small squares for accuracy purposes. From here up to here, there are 10 small squares, 10 small squares, 10 small squares. Use 10 small squares if you are to be accurate. Don't use it. Then you send out from 0 to 1. This one will give you an inaccurate value. But when you are using the 10 small squares, those are 2 centimeters, you can each locate the root with lots of accuracy. So the values of x starts from negative 3 up to 2. So which we can put our 0 at the center here. Then on the x-axis, in the interval, 2 centimeters represents 1. So this is 1, 2, 3. Then also do the same, negative 1, negative 2, negative 3 on this other side. Then you don't forget to label the x and y axis. Those axes must be labeled. The x and the y-axis, you must label them. Otherwise, if you don't label them, the whole graph will not make a lot of sense. So it will be meaningless if you don't label this axis. So you label the x and y-axis. So what we do, we plot the values of x against y. And I know at this level, most of us, many of us, knows how to plot the graphs. When you plot a graph of x against y against x, then you join the point. When you are joining, don't use a ruler. Like if you have plotted this point, you join this one to this one, join this one to this one, using the free hand. Join this one to this one, join this one to this one. You keep on joining two points, but when you are using a free hand. So don't forget, then you come and mark that this is a graph of y with an arrow. This is a graph of y is equal to 2x squared plus 3x minus 3. Then you see where the graphs, you can see now the graph intersect between x is equal to -2 and -3. The graph is cutting the x-axis between this interval. Also between 0 and 1, the graph cuts the x-axis between 0 and 1. So means that between this interval there is a real root, and if you are being required to locate the real root, this is where one of the real root lies, and another one lies here. So when you're using this scale which I used here, you will find that this one here, it is every small square is 0.1. So this is 1, 2. There are 7 small squares from 0. There are 7 small squares. So one of the roots is 0.7. Then when you come from this side, this is around 1. Where it intersects here, around the 1 small square there. Because if you are getting the root here, where it is between -3 and -2. So we counted the number of small squares. From here they are around, this is around 2 small squares. So it will be -2.2, and that is the root of the equation. For example, in case they have required us to locate the roots of the equation, you come and see where the line cuts the x-axis using your scale. Then you read the actual value which is there. So that's how it is done. Look at this other example. And still we are using a single graph method. We are using a single graph method to locate the root of the equation. Locate the root of the equation. This one here show graphically that there is a real root of the equation ex. This one here it is ex, like this, ex minus 2x minus 1 is equal to 0 between 1 and 2. Hence locate the root to one decimal place. So this one here, it is our y, ex minus 2 minus 1. So what we do, we choose an interval. They have given us an interval between 1 and 2. So we take that interval between 1 and 2, and we see if the graph cuts the x-axis within that interval. If the graph does not cut the x-axis between the interval 1 and 2, then we make a conclusion that there is no real root of the equation between the interval 1 and 2. But if it cuts the x-axis within that interval, then we conclude that there is a real root of the equation between that interval. So we come and say you start from 1, you choose a best interval. Like if you choose 1.1, 1.2, 1.3, 1.4, those ones will be very many, because we need to plot a minimum of 4 points. A minimum of 4 points. When you choose 5 or 6, those will go better. But if you choose 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, I mean that one. I mean 1.1, 1.2, 1.3, 1.4, it will be a very tiresome. But since when we use the 1, 1.2, 1.4, 1.6, 1.8, that one it is reasonably good, and we have plotted more than 4 points. So that is good enough. So we substitute in the values of x in the equation. Substitute 1, you get -3. Substitute 1.2 in this equation, you get -0.1. Using 1 decimal place is good enough. You only use 2 decimal places if, for example, if you substitute in the value of x is equal to 1. If x is equal to 1 and you get a value like 0.29, then you substitute x is equal to 2 and you get a value like 0.28. Then you substitute, get 0. Maybe x is equal to 3, and you get a value like 0.27. You realize that here you cannot use only one, you cannot round it off to 1 decimal place, and you say this is 0.3, this is 0.3, this is 0.3. Your graph will not make sense. So if you see that the values, when you round off, you are getting similar values, there you use 2 decimal places. But if you're not getting similar values like this one here, we round off negative 0.3, negative 0.1, 0.3, 0.8, you want decimal place because you are estimating where the root lies. It is not an accurate method of locating the root and even the, but it accurately locates the interval, but the root does not accurately locate the root. So we can approximate to 1 decimal place. Don't have to bother yourself using very many decimal places, unless if you find a situation like this one. When you round off, you get 0.3. Round off, you get 0.3. Round off 0.3 there, you use 2 decimal places. So we come to, after setting up our table of y and x, then we come and plot a graph. Don't forget to label the x and y axis. Those ones are very, very important. And use 2 centimeters. Those are 10 small squares. Don't use 5 centimeters like from here up to here. Say this is 1, this is 1.2. That one will be inaccurate. The root which you locate will be inaccurate. But when you use 10 small squares, this is 10, that is 10, that is 10, that's 10, that's 10. Those are 2 centimeters. So also on the vertical, you choose an appropriate scale. We started, this one corresponds to the horizontal. This one 0. These are the vertical axis is starting from 0, 0.5, 0.1, 0. So you choose an appropriate scale. And I know you are very conversant with this process of plotting the graphs, but when you are plotting, you make sure that you are using 2 centimeters, not 1 centimeter, because it will give you an inaccurate value. So when you plot a graph, make sure that you join these 2 points at a time, 2 points at a time, using free hand. Don't use a ruler, use a free hand. Then you form a graph, 2 points at a time, using your free hand. Then you will see that the graph is cutting the x-axis at some point. So this is 1, this is 2. So since the graph cuts the x-axis between 1 and 2, then you make a conclusion that there is a real root of the equation in the interval 1 to 2. Since after seeing that it is crossing the x-axis in that interval, then make a conclusion. Since the graph cuts the x-axis between x is equal to 1 and x is equal to 2, then there is a real root for the equation between that interval. The conclusion is very, very paramount. Then you come back to the graph and locate using our scale. This is 1.2 here. This is 1.4, 1.6. Then we realize that when you count here, this is 1, 2, around 2 small squares. 1, around 2 small squares. That's what? Because every small square, remember, every small square, because from here up to here is 0.2. So which means that from here up to here is 0.2. So which means that every small square is 0.02, because there are 10 small squares there. So when you are adding from 0.2 up to, you are adding 2 small squares, that is now 0.06. So this one here, our root where it is, this is where the root is. The root where point here, where the root is, it will be 1.2 plus 0.06. And that one will give us, it will give us 1.26. But when you go back to the question, when you add, you get 1.26. When you go back to the question here, they say, hence locate the root to 1 decimal place. So when you can say the root of the equation is 1.2 plus 0.06, but this one is supposed to be 1.26, but we round it off and we say it is 1.3 to 1 decimal place. So this is how you locate the interval and the root of the equation using a single graph method. We can also look at now the double graph method, 2 graphs. Because the question is, some questions are very tricky. They don't tell you use a double graph method. They say use graphs. That is a plural, means that you must plot 2 graphs. So we are given graphically show that the equation 2 sine x minus ln, this is ln, has a root between x is equal to 2 and x is equal to 3. Hence locate the root to one decimal place. So this one here, it is our equation, sine x, 2 sine x lead x is equal to 0. We say that in the double graph method, we split the equation into 2. We can take this one, this other side. When we move the lean x and we put on this other side, we shall remain with the 2 sine x is equal to lean x. So this side, y1 with 2x, 2 sine x, then y2 becomes lean x. Then you get the two graphs, the two tables. This is the table for y1, this is the table for y2. But the values of x should be the same. We said that we should get sure that it has a root between x is equal to 2 and x is equal to 3. So we look for values, suitable values within the interval from 2 up to 3. Then we substitute in the graph. But this one here, it is a natural logarithm on the calculator. I can show you how to get this value of the natural logarithm on the calculator. So on the calculator here, this button here, it is the button for the natural logarithm. This lean here, it is for the natural logarithm. So here, when it comes to like this graph here, when you are substituting, it is x is 2, then lean natural logarithm of 2 to get the y2. Then you come and replace lean, then you place 2 and you place the answer. You get 0.69, but we said that this one you can round it off. Since we're just estimating, you can round it off to 0.7. Then you use the 0.7 in the table. That is how we use the natural logarithm on the calculator. You repeat the same procedures to get the corresponding values. Also, use the button for natural logarithm to get the natural logaritm ln of 2.2. The next value there in the graph was 2.2. Then you get the answer, which is 0.788. But we said that since we are just estimating, you can approximate this one to 0.8, and that's why we have used the 0.8. So you repeat the same procedures. You repeat the same procedures. Repeat the same procedures for 2.4, 2.6, and you get the answers. Then this one here for sine, you make sure that the calculator is set to natural logarithm. I mean to radians. Set your calculator to rads. Like when you come here to press the mode, then you keep on pressing the mode. And then when you reach this one here, it is the radians. Don't operate when it is in degrees. So this one here, it is the rads. So you press the 2, then the calculator is set to radians. We say that every time you are having a trigonomical function. Every time you're having a trigonomical function like sine, make sure that the calculator is set to radians. Then you get the corresponding values of y1. Then you, after you go to your graph, remember we are plotting 2 graphs. You first plot one graph. Don't forget to label the x and y axis. The x and y axis must be labeled. You plot, this is the graph for y1. Then you also plot the graph of y2. It doesn't matter whether you use the x or you use the small dot and the circle, all of them works. But when you use the x, again, don't use the small circle like that, no. If you use the dot and the small circle, that is okay. Use the x, like this one here, use the x's, so the dot and the small circle. So don't forget to label. This is y2 is equal to lean, this is y1 is equal to 2 sine x. Yes, so when you plot those 2 graphs, join 2 points at a time, 2 points, 2 points, 2 points, 2 points, 2 points. Then you when these 2 graphs, the y1 and y2 intersect. Where they intersect here, that's where you locate the root. And the root here, or the point of intersection of these 2 graphs, it is at 2.6. So after, because the question was, they require us to show that the equation in this has a real root between the x is equal to 3. So after plotting our graphs and they appear like this, then we come and make a conclusion here. Don't conclude on the graph, you make a conclusion here that since the graphs y1 and y2 intersect between x is equal to 2 and x is equal to 3, then there is a real root of the equation between x is equal to 2 and x is equal to 3. You make that conclusion. The conclusion is very paramount. Then the root of the equation is 2.6 because they said we should give it to one decimal place. and you read it directly from the tables. And that's how we use the double graph method to locate the roots, the interval, and the roots of the equation.